All right, so looking at the electron configuration, some easy ones, some ions that form from cations. We know group 1 and group 2 always form +1 and +2 ions, right? So essentially we know that our metals in this column here always form +1. Our metals in this column here always form +2. And we can think about the electron configuration, right? 1s2, 2s2, 2p6, 3s1. And when it forms that ion, it's lost this electron over here, right? And that, what do we call that 3 when it's the highest n value?
Oh, the valence electrons.
That's right. So it's lost its valence electron. Calcium has how many valence electrons in it?
2, 4s2, two valence electrons, and the calcium ion loses them.
That's right. Calcium ion loses those valence electrons when it forms its ions. Now, we can also think about our valence electrons filling up subshells, right? So, for example, let's first look at these examples here of other elements losing electrons. Gallium, here's the electron configuration for gallium, right? 4s2, 4p1. So what do you think? How many electrons does 4s2, 4p1 have? Sorry, how many valence electrons, Fred?
Valence electrons?
Yeah.
2? Well, no, 1. Are they both count?
That's right. 4s2 and the 4p1, both of them count as valence electrons. Very good. So gallium will lose 1 in losing the 4p, right? But it'll also lose 2 additional ones in forming the in losing the 4s. The 2 4s's. Now, according to our energy diagram, both 4s2 and 4p1s are valence electrons, but according to our energy diagram, 4p1 are slightly higher in energy. Do you agree with that?
I don't know what you mean.
Well, remember, when we write our orbital diagram like this, right, for example, we had our iron here, right? Each orbital, or each subshell that we draw as we make this orbital diagram, goes a little bit higher in energy. So for S here, 3d10, in the case of gallium, we have 4p1. 4p1s would be slightly higher in energy than the 4s. And so the 4p's, which are higher in energy, will actually be lost before the 4s's. Okay? So that's a very important lesson as well. So, indium. Let's look at indium and try to do that same thing. What kind of ion do you think indium would like to form? Look at this electron configuration. Look for the valence electrons. How many valence electrons, Fred?
3?
That's right, 3 valence electrons. And which ones would it like to lose first?
I guess you said the 5p were higher in energy than the 5s?
That's right. So it's going to lose the 5p first and form a +1 ion.
But it can also lose the 5s too?
That's right. You can also lose the 5s2 and form +3 ion.
Okay.
So it's not surprising that gallium and indium don't generally are not found as a +2 ion. Does that make sense?
Oh, because the p orbital needs to lose its electrons first?
That's right. The p subshell needs to lose its electrons first. All right. So what's the correct electron configuration for the cesium atom and the cesium ion?
Can you bring up the periodic table?
So what do you think, Fred? Do you need to see the periodic table?
Yeah, show me the periodic table. It's kind of easy because mostly xenon, right?
Yeah, good observation. Xenon is the electron configuration, or the noble gas before cesium. Here's cesium right there, right? So xenon, all you need next to get cesium is what? What electron is that there?
That's in the S block, and the column is 1, 2, 3, 4, 5, 6. So 6s. So 6s1. So A or D, and then yeah. So xenon, yeah. So the answer is A.
Very good. The answer is A. So we found that this was the electron configuration for cesium, And then we see that when cesium loses an electron, forming a positive charge, it's that 6s1 that it loses. And look, it leaves behind a noble gas core, right? Which, again, results in a degree of stability. Okay, so let's look at another one, bismuth ion. Looking at the electron configuration, what ions might you expect?
Well, we got to get rid of the 6p3 first.
That's right. We want to get rid of the 6p3 first. It's highest in energy. And then we might also see scenarios where you get rid of the 6s2 and form a +5 ion. Okay? Now, there are a few exceptions every once in a while. Nickel is an example of an element that does some tricky things. And for that matter, elements in kind of this vicinity around where nickel is will do tricky things sometime. See, here's nickel. Let's try to write the electron configuration for nickel. Sorry, not just the electron configuration. We have the electron configuration here. Let's try to draw our orbital diagram for nickel. Now we have the electron configuration in front of us here, so it shouldn't be too hard. And we'll use the noble gas electron configuration so that we don't have to draw any extra. Okay, in terms of any extra the noble gas core. So we'll just look at we'll say, okay, so there's argon, and then there's the 4s2, and then after the 4s2, we have our 3d8 that we're going to add on here. 1, 2, 3, 4, 5. Okay, and then 4s2 has 2 electrons. 3d8 has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what do you think? What kind of ions do you think nickel would form? All right, let's zoom in a little closer here so we can look at it. What do you think?
Well, is it going to lose those 2 electrons?
Lose 2 electrons, 4s2. That's a reasonable assumption because they're the highest energy. So we might say maybe a nickel with a +2 charge. All right.
And then maybe a +5 by losing 3 more?
Okay, very good. So if it lost these 2, they're the highest energy. And if it lost these 3, then it would also kind of clean up that d orbital, leave a half-filled subshell, which is releases a degree of energy, offers a degree of stability. Okay, so those might be some thoughts that we would have looking at the energy diagram or the orbital diagram, electron configuration or the orbital diagram here. But it turns out that we don't ever see a +5 ion in nickel, but we do see a +3 ion in nickel. So what's happening is for nickel, if you just lose these +3 here, the ion finds itself in a situation where there's a significant enough degree of stability that it's willing to do that. It doesn't even lose those 4 s's, it just loses 3 electrons there, and it results in a stable ion. So you have nickel +2 and a nickel +3 as possible ions because of that. Now, this isn't a scenario where it's very predictive. However, it is explanatory after the fact, right? So both of those abilities to either predict or explain are helpful and valuable based on what we've learned in our previous chapter, right? We can make those kinds of predictions now. All right, so these are opportunities for you at home to predict the ions of iron, zinc, and thallium, Tl. All right, so thallium is element 81, zinc element 30, right? Iron element 26. So I'm going to let you guys work on this at home, and then when you're done, we'll go through it together. Okay, what do you think, Fred? Did you get to work on it?
We already did this iron one.
Very good. We did do the iron one. And it helps to have our electron configuration in front of us. And we said what kinds of ions would want to be formed.
A +2,
Very good, a +2.
and then a +3.
Very good, a +3. So those were our ions that we could predict based on the electron configuration. Based on the electron configuration of zinc, what kinds of ions would you predict?
Well, this one I only said +2 because it would have to be a +7 if it lost 5 more and got a half-filled D cell, and I just didn't think that was likely.
Okay, that's good. That's a good observation. And that's an understanding of why, when I have zinc chloride, people never call it zinc 2 chloride, simply because zinc always forms a +2 ion. All right. It's okay to call it zinc 2 chloride, but that's why people don't call it zinc 2 chloride. Good. How about the thallium?
Thallium, it looks like a +1 and a +3.
Very good. A +1 and a +3 ion. Excellent. Good work.